In Oita, Japan, stands the largest dome on Earth. It is an architectural marvel built from steel, Teflon, and titanium. It covers a stadium big enough to comfortably seat over 40,000 spectators. At the flick of a switch, the roof can open and close like a gigantic eye. The Oita Dome is a pinnacle of structural engineering. Oita owes its success to 6 iconic domes. At the heart of each lies a major technological innovation that allowed engineers to build ever bigger domes. One by one, traveling up the scale, we'll reveal the incredible stories behind these structures and the inventions that allowed them to span ever greater distances. Six ingenious leaps forward, from big to bigger, into the world's biggest. Oita is a city like many others in Japan. But just outside its gates stands a structure that is the envy of cities throughout the world. Oita Stadium, the largest freestanding dome in the world, and home to Oita Trinita Football Club. Stretching over 270 meters across and reaching nearly 20 stories high, Oita is the ultimate leap in a series of historic engineering breakthroughs. To understand how the Oita Stadium can be this huge, we must travel back in time to ancient Rome and an iconic building that has stood for nearly 2,000 years. The Pantheon. In the 2nd century AD, the might of the Roman Empire stretched across 3 continents. Emperor Hadrian wanted to mark his dominance by building a colossal temple to the Roman gods, the Pantheon. And he insisted it be capped with the biggest dome in the world. The Romans believed they had just the right building material for the job. They had discovered that if they took lumps of rock and embedded them in a special mortar, they ended up with a substance that was extremely tough and could be formed into almost any shape. They called it concrete. Ed McCann is an engineer who knows all about this Roman stroke of genius.
Now, concrete really has just been invented, but they're building Rome with it. It's the new wonder material. They build the Forum with it. They build parts of the Colosseum with it. And Hadrian decides that he wants to build a dome out of it too.
Concrete is very durable, but also very heavy. Had the Romans built the Pantheon with it, the dome would have weighed over 20,000 tons. Such a load bearing down would have caused the base of the Pantheon to splay outwards. The result would have been catastrophic. To prevent such an embarrassment, Hadrian's engineers had to find a way to make concrete lighter.
Roman concrete is typically made using this sort of aggregate. It's a really dense, heavy volcanic rock called basalt. And it makes the concrete very strong, but it also makes it very, very heavy. But Rome is also very fortunate because it's near some volcanoes. And this stuff here, pumice, is like the froth on a cappuccino coming out of a volcano. It's lava that's aerated with tiny little bubbles in it. And in fact, it's so light, it floats.
Using lightweight concrete helped to cut the weight of the dome by 1/3. But Hadrian's masons were concerned that this was still not enough, so they tried to shave off even more weight. They cut down on concrete wherever they could. They tapered the walls of the dome so that they were thickest at the base and thinnest at the crown. They even left the apex open to the elements to save concrete. And they hollowed out the panels that formed the ceiling to save even more. Together, these tricks reduced the dome's final weight to 5,000 tons, a mere quarter of its original weight. But engineers were still worried that the base of the dome might splay outwards. So they strapped 7 concrete rings around it. These tension rings held the walls in, like the steel hoops round a wooden barrel.
I mean, here we've got a building that's nearly 2,000 years old. It's made out of unreinforced concrete, made out of bits of volcanic ash and lime, built by men who had no mechanical plant to talk of, 2,000 years on, it's still the biggest unreinforced concrete dome in the world.
The technology pioneered by the Romans is still used on the Oita Dome today, only on a much bigger scale. Today at Oita, engineers face a similar problem to the men who built the Pantheon. They too must make sure that their dome doesn't collapse under its own weight. Because of its gently curving shape, the edge of the dome meets the foundations at a shallow angle. This puts tremendous sideways pressure on the concrete foundations. If the engineers simply put the dome on the ground, it would splay out and collapse. So like Hadrian's architects, they will use a concrete tension ring to hold the walls in. But they fear that to contain their 12,000-ton dome, they will need to build a ring so huge that it will be too big to fit on the plot and block access to the stadium. So they decide to dig down and use the surrounding bedrock to provide extra bracing. Now they can build a much thinner tension ring to hold up the roof. But on the scale of Oita, it's still pretty big. Pouring the concrete for the tension ring takes over 6 months. Engineers lace the concrete with thousands of tons of steel bars to strengthen a material that would otherwise be brittle. Then they embed the steel supports for the roof trusses into the concrete. They must lay them with the utmost precision. If they're misaligned by even a small amount, then the roof trusses will not slot neatly into position.
I'm standing at the base of one of the giant arch trusses supporting the main stadium roof. Now these arches are supported in turn on a tension ring, and this footing behind me just gives you some idea of how huge this tension ring is.
Thanks to lightweight concrete and some heavyweight thinking, Hadrian managed to build his temple to the gods. It took over 1,000 years before someone tried to better it. To build the 45-meter-wide dome of Florence Cathedral, engineers would have to teach an old building material new tricks. In the late 14th century, the city of Florence was in a bit of a pickle. It had spent 100 years building a magnificent cathedral to demonstrate its cultural superiority. But there was one thing missing: the roof. City officials wanted the cathedral to be crowned with a big brick dome, but nobody had any idea how to build it.
They build a cathedral 40 metres high with a big hole in the middle. This tells us a lot about their confidence, their utter self-belief that they can find someone who will know or figure out how to build the world's biggest dome.
Like the Pantheon before it, the dome in Florence would need wooden scaffolding to support the structure during construction. Engineers calculated that their scaffolding would need 700 trees, some of them over 100 meters tall. But there were no trees this big around Florence. So they had to find a different way to shore up their dome while they built it. The years dragged by, and still the cathedral was without its dome. Constructing one without scaffolding seemed impossible. Then, in 1418, a local clockmaker called Filippo Brunelleschi stepped forward.
Brunelleschi is actually your archetypal Renaissance man. I mean, he's almost 100 years before Leonardo, and he does it all. He's a sculptor, he's an artist, he invents cranes. He comes here to Rome and spends 13 years digging away in Roman ruins to understand their technology. He figures out whether things are going to work by looking at stuff that already has worked. He measures everything, and he takes this understanding back to the great project of his life in Florence.
Brunelleschi built a wooden model of the dome to prove to city officials that he had cracked the problem.
So Brunelleschi goes in and they say, well, how are you going to do it? He says, I'm going to do it without any scaffolding at all. I am going to build the dome off itself, and we'll stand on the edge as we go along. And they just laugh him out of town. I mean, they ridicule this guy, and this is a proud man, you know, and he's absolutely ridiculed. It's said he couldn't even go out in the street because people would just stand and laugh at him. But he's determined. I mean, you know, he may be ridiculed, but he's determined, and he keeps nibbling away at them. He just says, you're wrong. You're so foolish, you don't understand. I'm right, you're wrong. And eventually they say to him, all right then, smarty pants. So they give him the gig. They give him the big dome.
Brunelleschi closely guarded the secret of the dome's construction, but this is how we think he did it. The most critical stage of the project came when the dome walls started leaning inwards and the bricks were in danger of sliding off. To build on such a steep slope, Brunelleschi laid some of his bricks vertically so that they stuck out from the workface. These vertical bricks acted like bookends that wedged the horizontal bricks in place. But even with Brunelleschi's clever method, it took 300 men over 15 years to build the dome. Florence Cathedral was finally topped out in 1446. Sadly, Brunelleschi didn't live to see the day. He took the secret of the dome's construction to his grave. But his engineering marvel still dominates the Florence skyline and remains, to this day, the largest brick dome ever built. Oita Stadium, Japanese engineers have also found a way to build their dome without a forest of scaffolding. They do most of their construction on the ground. They weld together hundreds of sections to make the main trusses for the roof. But now they have to lift and slot them into place. This is quite a job when they can weigh as much as 110 tons. Conventionally, tower cranes with a long reach are used to shift heavy building materials. But at Oita, these cranes would need to be able to stretch over 300 meters to reach the far edges of the building site. A crane with a boom this long would not be stable. So the developers put their crane on tracks so it can move about. To stop it from toppling over, they load the back with a heavy counterweight to lower its center of gravity. 4 of these cranes lift the trusses into place. The Japanese complete their dome in a matter of months, rather than the years it took Brunelleschi to build his. Back in 1446, Brunelleschi's dome for Florence Cathedral pushed bricks and mortar to the limit. To crown the West Baden Hotel in Indiana with an even bigger dome, engineers would have to find a better building material. At the turn of the 20th century, West Baden Springs in Indiana was one of America's most popular spa towns. Local entrepreneur Colonel Lee Sinclair wanted to cash in on the boom and build a luxury hotel for the wealthy visitors. He demanded that his grand building should be finished off with the biggest dome in the world.
Lee Sinclair, the hotel's owner, had traveled to West Baden, Germany, to see some of the world-class spas there. And he had also seen several of the domes in Europe, and he was asking these architects in the United States to design a dome structure. He already had the size in mind, 200 feet. Most of the architects that he interviewed turned him down and said, you know, Lee Sinclair, at 66 years old, you're a fine guy, but you're crazy, it can't be done.
Sinclair's architect knew he couldn't build such a big dome with bricks and mortar, but he found inspiration at the cutting edge of 19th century technology.
What we've got here is it's a bridge, more or less, and on the top we've got a deck which might have had a railway running on top of it or a road, but it's all held up by a steel structure. And I'm going to take the top off and we'll have a look at the steel structure. And what you see here is quite surprising really to the 19th century person, because it's a really light, open structure. If you compare this with a masonry structure, which would essentially have been solid with masonry, it's really light. And the building designers looked at that and said, well, I can turn that into a building.
And this is exactly what Colonel Sinclair did. He turned to a bridge engineer to help him build his dome. He locked 6 bridge trusses around a central hub. These supported a roof made from tiles and glass. Together, they formed the grand atrium of West Baden Springs Hotel. The forces generated by the weight of the roof are channeled along the trusses and converge at the hub, also called the compression ring.
We are in the geometric center of the compression ring, which is like a drum, 10 feet in diameter, 10 feet high. And you can see each truss is riveted, and that's where all the compression comes.
Steel is very strong and light, but it has an Achilles heel. It expands in heat.
And we've actually measured from a very hot day to a very cool evening, this dome will travel in any direction 1.75 inches.
If a steel dome is locked to the masonry, heat expansion becomes a serious problem. On hot days, the heat from the sun will make the steel expand twice as much as the masonry. This could tear the roof from the stone pillars with disastrous results. To prevent this, engineers at West Baden attached rollers to the base of each truss. These move with the steel structure, allowing it to grow and shrink as it heats and cools over the course of the day. The magnificent crystal atrium under Colonel Sinclair's dome draws guests from across the country to West Baden Springs. To this day, they are left in awe of his monumental achievement.
This building did have probably the first high-tech design of steel trusses. It's almost like when you walk through here, take off your shoes, for you walk on holy ground.
The legacy of the bridge designer is plain to see at Oita today. But the Japanese have taken the idea to the extreme. To span the huge expanse of the Oita Stadium with a roof, the Japanese builders have little option in their choice of building material.
For the roof structure on Oita Stadium, the engineers decided to use steel. Steel is good for spanning large distances because it has a good strength-to-weight ratio, so the members don't become too heavy even if they're very long.
But as Oita is over 4 times bigger than the West Baden Dome, the Japanese can't follow its simple hub and spoke design. It will make the roof so heavy it would collapse under its own weight. That's why Oita needs clever geometry to make its roof stand up. 7 bridge-like trusses form the core of the roof. A ring of steel binds the bridge trusses together. Finally, a huge spine truss runs the whole length of the stadium to lock all the elements into a rock-solid steel skeleton, strong enough to carry its 12,000-ton skin. And to lighten the whole structure, the engineers make their trusses hollow. Back in 1902, Colonel Sinclair's dome at West Baden showed that steel was the key to making domes bigger. Soon, stadium designers began to take notice. In Houston, Texas, the local baseball team wanted to do what nobody had done before: play their games in air-conditioned comfort. So they planned a stadium with a huge domed roof that would keep the weather out but let the light in. In the late 1950s, the oil boom was turning Houston into one of America's super cities. But any major city needed an iconic sports stadium, which Houston was sadly lacking. So engineers began to build a baseball field covered by an enormous transparent dome. They called it the Astrodome. To save weight, they glazed the dome with a material that had proved itself in the Second World War. Perspex was a new type of plastic that weighed half as much as glass. It was perfect for the cockpits of bombers. Perspex is light, strong, and crystal clear. Light rays pass right through it, which created a surprising problem for the designers of Houston's Astrodome. The unimpeded sunlight would have cast harsh shadows on the field, which could have troubled the players. To solve the problem, the designers added a layer of microscopic prisms to the Perspex. These diverted the rays and diffused the light. They fitted 5,000 of the new panels onto the roof of the Astrodome to spread the light evenly across the whole stadium. When the Astrodome opened in April 1965, it was hailed as an architectural triumph. But the players were not so fond of it. One player trying to catch a high ball got nowhere near it. He blamed it on the glare from the Perspex roof. In a normal stadium, catching a high ball is not a problem. Because the arena is open, the sky and the field are almost equally bright. In the Astrodome, the steel framework of the roof blocked out some of the daylight and left the field in relative darkness. But the light coming through the Perspex panels remained bright. When players looked up from the dark field to the bright skylights, their eyes were simply overwhelmed by the glare. The Astrodome finally conceded defeat and simply painted over the Perspex panels. Now the players could see the ball, but the lack of light killed the grass. In the end, the groundsman laid a brand new field, made from a grass that needs no light, AstroTurf. Today at Oita, the designers will not settle for anything less than real grass. Their roof will have to let in the light without blinding the players. First, they build the steel matrix onto which the roof membrane will be fixed. This is constructed in sections on the ground and then craned into position. Once the framework is complete, the engineers must find the right material to cover it. They choose a sturdy glass fiber membrane coated with Teflon. Light rays enter the outer Teflon layer and scatter when they hit the glass fibers inside. The engineers can precisely control the amount of light passing through by adjusting the density of the glass fiber weave. This way, they can give their roof the perfect transparency. Just bright enough to light up the pitch without blinding the players.
Well, what I like about Oita Stadium is this marvellous sense of openness and airiness that you get inside, even with the roof closed. So much light passes through that it feels almost as if you're outside. There's also a deliberate gap around the perimeter, and this both allows fresh air to pass into the space and at the same time makes it feel even more airy and effortless.
But as well as letting the light through, the membrane must also be strong enough to withstand the battering of wind and rain. So before the Teflon membrane can go onto the dome, engineers need to test its strength. To stretch the membrane to the limit, they load it with children's paddling pools full of water. Only once it's passed the paddling pool test can the membrane be rolled out across the dome. Since it was installed, it has stood up to everything nature can throw at it, and the grass beneath continues to thrive. Back in the 1960s, the success of the Houston Astrodome inspired stadium designers to build even bigger domes. But bigger crowds brought a new challenge. The designers of the colossal Georgia Dome in Atlanta had to make sure that their stadium didn't become a death trap. In May 1985, disaster struck Bradford City Football Club. Without warning, 3,500 spectators who were packed into a wooden grandstand were engulfed in flames. Within minutes, the stand burned to the ground, and 56 people lost their lives. Many died from inhaling smoke. So when architects in Atlanta designed the Georgia Dome 4 years later, they knew that such a fire would be even worse in an enclosed space.
One of the big challenges with covered stadia is fire. And fire generates smoke, and that really is the cause of the problem. And in this experimental setup, what we're going to do is explore what happens when there's a fire in a stadium. Now, here we have our domed stadium, and you've got to imagine thousands of people sitting around watching their favourite band when, in the kitchen, a fire starts. And so I have down here my little smoke machine, which is going to be creating the smoke that you would get in a fire. So imagine there's the fire, and you see the smoke immediately flood into the space, and it rises up because it's hot, up to the roof, and then it flows down the sides. And if you're sitting in seats up around here, rapidly you can't see anything, you can't see your way out, you can't breathe, and panic will begin to ensue. So what can you do about it? One thing we can try is to make a hole in the roof, which I'll do by taking this little strip of tape off, and popping a fan on top. So here we have it, my fan, which I'm going to pop onto the top there, and I'm going to switch it on around the back to see what happens. So the fan's running up, and quickly you can see a little bit of smoke coming out there. And if we look down into the dome, we can see even though the fan's going, the air is still full of smoke. So why is that? Well, the answer is there's no throughput of air here. There's nothing flushing this stuff out. What we need here are some vents at low level. So I'm going to take my ventilation covers off. And now we see a lot more smoke coming out of the top, and rapidly the dome begins to clear out. So people can see again and they can breathe again. They can make their way to the exit and all is well. It really is just as simple as that. You need something to suck the smoke out, but you also need a through flow of air. So you need some ventilation at low level to let air in. There we are.
The engineers at the Georgia Dome put powerful fans in strategic positions. As soon as a fire is detected in the stadium, the emergency ventilation system kicks into action. Fans mounted in the ceiling begin to spin. Simultaneously, air intakes above the exits flip open to create a through draft. Fresh air is drawn into the stadium, and smoke caught in this current of rushing air is sucked through the fans and dispersed harmlessly outside. Oita Stadium can hold 43,000 people, so the prospect of their dome filling with smoke is terrifying. Because the roof can open at Oita, smoke disperses quickly. But the designers here have gone a stage further. They can snuff out a fire the instant it breaks out. Conventional fire detectors work by detecting smoke. But in the time it takes for the smoke to reach the sensors, the fire may be raging out of control. Oita's system doesn't need to look for smoke. It can detect the actual fire. When a fire burns, it produces hot carbon dioxide. The gas emits infrared radiation with a unique heat signature. Sensors constantly monitor the stands for any sign of the telltale radiation. Infrared travels at the speed of light, so the sensors can detect a fire almost instantly. Then a computer automatically triggers the response. Robotic firefighters. To keep spectators safe, Oita Stadium has one of the most advanced firefighting systems in the world.
Okay, we're going to do a quick test to check the response of the fire prevention system in the stadium. There we go. Torch is nicely alight. And into the fire. There we are, and we're nicely alight.
Within seconds, the water guns automatically take aim. The fire produces hardly any smoke, but the invisible carbon dioxide gives it away. Now the guns show their awesome firepower. They shoot 4,000 liters of water a minute at a fire 80 meters away. It's no contest. The fully automated firefighting system at Oita will make sure that all the 43,000 spectators are well protected. They may get wet, but they'll be safe. In Georgia back in 1992, designers showed how to get rid of deadly smoke in an enclosed dome. With the fire problem under control, sports Superdomes could now afford to grow even bigger, and their designers became even more demanding. The architects of the world's biggest dome, the 274-meter-wide Oita, want to crown their masterpiece with a real eye-catcher, a roof that can open at the touch of a button. The first attempt to build a retractable roof came in 1987 with the Olympic Stadium in Montreal. Engineers built an inclined hollow tower nearly 170 meters high. They threaded steel cables down through the tower and wound them round winches. They attached the other ends of the cables to the roof, an enormous sheet of Kevlar weighing 65 tons. On sunny days, technicians would wind the winches to raise the roof and allow light and air inside. In cold or wet weather, they'd simply drape the sheet back over the stadium. It was a beautiful design, but only on paper. One day when the technicians raised the roof, it ripped. And over the next 10 years, it broke down so often that they finally replaced it with a fixed roof. The engineers building the retractable roof in Oita simply cannot afford such a failure. So unlike their counterparts in Montreal, the Japanese pick an extremely simple design for their stadium.
For the roof structure on the Oita Stadium, the engineers decided to use a spherical geometry. The sphere is a well-defined mathematical form, so it simplified the steel manufacturing and also allowed the movable part of the roof to be easily moved over the permanent part of the roof, a sphere moving over a sphere.
The engineers want to build the moving roof in two sections that open and close like a giant eye. They install 50 trolleys to carry the sections. These run on rails built into the trusses and are winched along by cables. A high-tech railway moving over 2,000 tons of steel, Teflon and glass fiber.
I'm standing at the moment in the main ring truss running around the opening to the stadium, and the retracting part of the roof is being closed. This takes about 20 minutes to open or close using cables running around pulleys. And I think you can see behind me perhaps that wheel up there, which is rotating slowly. That's carrying one of the cables down into the basement to the winches which lift the roof into position. In the reverse direction, when the roof is opened, the roof moves back under its own weight, using a braking system to control the speed.
The trolley system at Oita is an elegant solution, but the engineers must make sure that all trolleys work in perfect harmony. If under the heat of the sun, some of the steel rails expand more than their neighbors, the trolleys will be thrown out of alignment and the mechanism will jam. So the designers install sensors that compare the position of the trolleys on each rail. If the trolleys on one rail are out of step with the others, a computer will adjust the speed of the winching cable to bring them back in line. At least, that's what the designers hope.
I think you can imagine the tension in the designer's mind as this was done for the first time. Thousands of tons of steelwork being moved across many meters of rail. If one of these wheels or trolleys came out of position, then we could get a situation where perhaps one of the wheels slipped off the rail, and obviously that would be a very serious event.
The sliding roof over Oita Stadium is a triumph of engineering. It's bigger than 3 football pitches and weighs more than 15,000 sumo wrestlers. Yet the clever trolley system makes its movement look effortless. This is the crowning glory of an amazing piece of architecture. With its structural elegance and multitude of high-tech features, the Oita Dome is truly in a league of its own.
The designers were trying to achieve in this space what they called a second nature, or a symbiosis with nature. And I think they've achieved it.
Indebted to the engineering feats, innovations, and mistakes of the past, this really is the ultimate Superdome. Until someone builds an even bigger one.